Hello, future engineers and physicists. Today, we are tackling a topic that separates the top-tier candidates in competitive exams, variable mass dynamics. While the basic version of Newton's second law, F equals ma, is sufficient for constant mass, true mastery in the JEE or Gaokao requires the generalized second law, F equals dp by dt. By applying the product rule to momentum, we derive two distinct terms, m dv by dt, representing standard acceleration, and v dm by dt, representing momentum transfer. This second term is non-zero whenever an object continually gathers or deposits mass. In an exam setting, this is the invisible force students most often miss. Let's analyze a classic challenge problem, the falling chain. A flexible chain of mass m and length L hangs vertically, just touching a scale. When the top is released, what is the force on the scale at the moment a length x has landed? Many students fall into the static trap, assuming the scale only measures the dead weight of the links resting on the table, or lambda xg. However, the physical reality is a paradigm shift. The actual measured force is exactly 3 times the static weight, or F equals 3 lambda xg. The scale isn't just supporting weight, it is actively destroying the downward momentum of every falling link. To solve this, we must deconstruct the force into two components. First, consider component 1, dead weight. The portion of the chain already resting on the table exerts a simple static gravitational force, F static equals lambda xg. Next, we reveal component 2, momentum transfer, also known as the dynamic hammer effect. Every falling link hits the table with the velocity v equals the square root of 2gx. The force required to stop this mass flow instantly is calculated as v times dm by dt, which simplifies to 2 lambda xg. When you sum these components, 1 lambda xg for weight and 2 lambda xg for impact, you arrive at the total force of 3 lambda xg. This ratio is a high-yield fact for your exams. The dynamic impact is exactly double the static weight. This logic extends to mass accretion on a conveyor belt. Even if the belt moves at a constant velocity, the motor must supply a continuous horizontal force. Because the system constantly absorbs new mass, the motor must provide a force F motor equals v times dm by dt to accelerate that mass from 0 to the belt's velocity. Conversely, we can explore mass depletion via rocket propulsion. Instead of stopping new mass, a rocket violently ejects internal mass to change its own momentum. Here, the forward thrust, F thrust, is entirely dependent on the exhaust velocity, u, and the mass depletion rate, dm by dt. This is the fundamental push that overcomes gravity. We conclude with Tsiolkovsky's rocket equation. By integrating the thrust equation, we find that final velocity is bound by the natural logarithm of the initial to final mass ratio. This explains why rockets must be overwhelmingly comprised of fuel to reach orbit. The golden rule for your exam preparation is simple. Never trust a static picture. When a system gathers or deposits mass, you must triangulate between kinematics, statics, and momentum conservation. Master the invisible transfer of momentum, and you will reconstruct physical truths that others miss. Good luck with your studies.